Hello everyone, welcome to this third question in the challenges series, Physics Advanced Problems. This question is also taken from Pathfinder, rotation chapter, challenge your understanding, third question. Let me read the question. A light rigid square plate of side L is suspended horizontally with the help of 4 identical vertical wires. So the last question was legs, now it is wires, we are hanging it from the ceiling, affixed at their lower ends on each of the corners of the plate. The upper ends of the wires are affixed to the horizontal ceiling. All these wires are elastic, that means they can deform and have very high force constant. Very high force constant K meaning they will deform, but the deformation is negligible compared to the dimensions of the plate we have here. Now the question is, we need to find the region of the plate in which if you stick a load much greater than that of the plate, meaning plate mass can be neglected, everywhere will remain taut. So the tensions should remain greater than or equal to 0. So acceleration of free fall is g. Okay, so that's our question we have. So here the assumption is mass of the plate is neglected and strings are vertical, hanging from the horizontal ceiling, and we can take anywhere. We need to keep a very large amount of mass on the plate in such a way that all the wires would be taut in the sense straight, they are not supposed to slacken. So whenever you try to stretch the strings, they become taut. Whenever you tend to compress the string or relax the string, they are going to slacken. Slackening is what is not expected here. That's a condition we have here. So again, let's get into this top view. Imagine this is a square plate we have. The corners I am writing it as 1, 2, 3, 4. So this is a horizontal view. It's a horizontal plane we have. I have taken x axis plus x and minus x. I have taken y positive down in the sense on the screen down here. So that if I use right hand thumb rule, I cross j should be into the screen. So z I am taking into the screen there, x, y, z. That's a square plate we have. I have taken the origin to be center of the square plate. Now where should I keep the point so that none of the strings would slacken? That's a question here. So the possibility is that you may have only one point like that. That point would be at the center. If you place the mass at the center, by circular symmetry, all the strings would elongate by the same amount, so there won't be any slackening. Or if required, you might have lines. If you have lines, right, if you have one line in one quadrant, you have equivalent type of lines in all the quadrants. You will have 4 lines possible, or otherwise you may have entire square plate. Anywhere you can keep it in such a way that no string would get slackened. That's also possible. Or it's also possible that in first quadrant you may have, let's say, this kind of a curve. First quadrant you may have a curve something like this. If you have a curve like this, then by circular symmetry in the other quadrant you must have this kind of curve, similar one. So you can have that circular symmetry. So you will have something like this, you will have it. So you don't have to study all the 4 quadrants. If you can identify just one quadrant, then by symmetry we can understand all other quadrants also. So I will just remove them. And we need to identify the region, meaning we need to identify the coordinates of points x comma y which satisfy the condition in such a way that if I place the mass capital M there, none of the strings would get slackened. So I have taken coordinate system like this, and we have to find the relation between x and y so that none of the strings get slackened here. So I have added little more here, just look at it. So the right end would be x equal to plus L by 2, left end would be x equal to minus L by 2. Same way the lower one would be y equal to L by 2 and the upper one is y equal to minus L by 2 on my screen here. This is a horizontal plane for the question that we have it. So that's a diagram we have. I have just drawn 2 yellow lines to indicate that point P where we are going to place mass. That P can be anywhere x comma y, that's where I am going to place mass. So if you look at the forces, right, the forces are T1, T2, T3 are the forces, T1, T2, T3 and T4 are the forces, tensile forces. They will be pulling, they will be out of the page, meaning upward direction. Mg is into the page, that means it is into the board. So gravity is into the board. gravity is into the board. That's what we are assuming here. So there are 4 forces vertically upwards and 1 force mg balanced by these 4 forces into the page. Okay, that's the basic diagram. Let's go on little more in details. So now because of the forces, let's say the tip, depending on where you are keeping it, the particles, so the ends would go different displacements here. They said that spring constant is pretty high, so that is why, because the spring constant is very high, you can see the displacements along z axis have to be small, they are not pretty large. So you can see those displacements z1, z2, z3 are the displacements I am considering, z4 and z0 is the displacement of origin we are considering. These displacements are much smaller than the dimensions of the plate here. Because of the small displacements, you can neglect the tilting of the strings. Even though the plate is tilting, the angles of tilting is small, so you can assume the strings to be almost vertical, so they need not be tilted or made some angle. Even if they make small angles, that angle can be neglected. That's assumption here, where cos theta is equal to 1 approximately. That assumption we are considering here. So now I will take certain projections here. What I will do is I will take a diagonal 1 and 3 which is passing through O, 1, O, 3. If I take that particular diagonal and focus on it, so that line would be tilted, let's say, in this direction. So end 1, let's say, has come down by z1 distance, and O center would have come down by z0 distance, and point 3 has come down by z3 distance, like that. So then, because it is a rigid body, so this is one condition I am using here, because it is a rigid body, so displacement of the midpoint is the arithmetic mean of the displacements of the ends there. Displacement of 1 plus displacement of 3 upon 2 will be displacement of O there, because it is a midpoint. That is a rigid body constraint. So I am not going to explain it in much in detail. I hope you understand it. If you require, we will take that as a separate session for it. So similarly, you look at the other diagonal 204, the other diagonal, and let us say 204 are having displacement z2, z0, z4 in vertical direction. Again, O is the midpoint. So it is supposed to have displacement which is the arithmetic mean of displacement of 2 and 4. So we got z0 for 2 expressions, z1 plus z3 by 2 from the first diagram, also equal to z2 plus z4 by 2. By comparing that, I will get one equation. This is the equation I am getting from rigid body constraint. So that is first part. Then I will use a translational equilibrium. So there are 4 forces vertically upward, T1, T2, T3 and T4. Summing up should balance mg. So you get this relation, and we are assuming the strings to be identical. That is the assumption I am taking. I am not sure whether they had given it or not. They had given, you see, identical wires they had given, fine. So if that is the case, all of them will have same spring constant or force constant. So from there, k into z1 is the spring force in T1, string force, k into z2 is the force in T2, and so on. So if you take k to the other side, we get the second equation. So the second equation comes from translational equilibrium. 2 equations are done, but we have 4 unknowns here, z1, z2, z3 and z4. See, what is the condition we have to use? All these z's I will calculate all the 4 and make sure that none of them become negative. z1 has to be non-negative, z2 has to be non-negative, z3 has to be non-negative, and so on z4. So we require 4 equations to find these 4 unknowns, and out of that I got 2 equations, one from rigid body constraint, another one is from translational equilibrium. I have to get 2 more equations and find all these z's and make sure that they are always greater than or equal to 0. This is a condition I am going to use here. Okay, next let us go to the next slide here. Now I am going to use rotational equilibrium. When you are using rotational equilibrium, torque we will write. Torque about a point you can write, torque about a line you can take it. So I would like to take torque about this line. Let us say this is L1 here, this yellow line, and this is L2, and I am taking this as a first quadrant, this is Q1. So in first quadrant, if a point is there, right, this is Q1, then you have x is positive and y is also positive. So if you have, this is x, this is x, then this has to be, this is L by 2 anyway. So then this total distance will be L by 2 plus x, then automatically this will be L by 2 minus x, you have it. So that is understood. Similarly in y direction, if you consider, so this is y for you, because this is origin, no? This is y, and this distance is L by 2. So L by 2 plus y would be the other distance from L1. Same way you can calculate L by 2 minus y. So we got the distance of the lines from the edges, either edges. So now I'll write torque equation. So I'll calculate torque about the line. Let's say torque about L1 I'll calculate. When I calculate torque about L1, so one side of L1 I have T2 and T1, which are at the same distance, perpendicular distance L by 2 plus y. They try to tilt it in this direction. And on the other side of L1 you have T3 and T4, which are at equal distance L2 minus y and L2 minus y. So if I take that, I think this is going to be L2, this is L2 and this is L1. Anyway, equations are similar only. So about L1 if I calculate, I will have this Z1 plus Z2 into K, that is a spring force or a string force, into L by 2 plus y, that is a torque due to them. That should be counterbalanced by the other forces. You have Z3 plus Z4 into K, this is a force from T3 and T4. They are at a distance L by 2 minus y, they should counterbalance it. You will get one equation from there. And same way torque about L2 if you calculate. So you have on one side of L2 you have T1 and T4. T1 plus T4 into this L by 2 minus x is trying to tilt in this direction. T2 and T3 are one side. T2 plus T3 into L by 2 plus x will be in opposite direction. So I got third equation and fourth equation. These two equations are obtained using rotational equilibrium about any axis. So torque due to mg will be 0 because mg is passing through these lines there. I have four equations now, two equations from rotational equilibrium, one equation from translational equilibrium and one equation from rigid body constraint. So we got all the four equations, enough to solve four unknowns. I have listed down them and now I am trying to simplify it. What I will do is I will take these two equations first, right? Z1 plus Z2 plus Z3 plus Z4 equal to mg by k, and Z1 plus Z3 equal to Z2 plus Z4. So if you compare them, you will get this equation 1 and 2 together. And then what I will do is I will simply use componendo dividendo on third equation. Componendo dividendo. A plus b equal to c plus a by b equal to c by d, then you will have a plus b by a minus b equal to c plus d by c minus d. That idea I am using it, and cross multiplying it I will get one equation. And same way one more equation from the fourth one, again use componendo dividendo for fourth equation, and then cross multiply, you will get this. So wherever you are getting Z1 plus Z2 plus Z3 plus Z4 is nothing but mg by k, you can substitute there. So you can comfortably solve these linear equations. I am just explaining it. You will do it much better if you do it on your own. So now if I get that, I am getting these 3a and 4a. Let's say 3 is the expression given. I use componendo dividendo. I got this 3a, and same way 4a. Solving this, I got Z4 minus Z2 equal to mg by Lk into x plus y, and 1 and 2 together I already got Z2 plus Z4 equal to mg by 2k. Add them together, you see that Z2 will cancel out. Then what are you left with? 2Z4 equal to mg by k into 1 by 2 plus x plus y by L. That should be greater than or equal to 0, that is a condition. It has to be taught, no? So that means whatever is in the bracket, that has to be greater than 0, and that if you rearrange it, I get this x plus y has to be less than L by 2, x plus y has to be less than L by 2. So what do we do? First you write x plus y equal to L by 2, that is going to be this line. So this is x, this is y. X plus y equal to L by 2 meaning it has got a negative slope, and when x equal to 0, y equal to L by 2, y equal to 0, x equal to L by 2. So x intercept and y intercept both are L by 2. This is the line I got. And then the region less than or equal to meaning within the on the origin side, that's a shaded part. I have shaded that part. So x plus y less than or equal to in fact it shouldn't be greater. Then we have this situation. Now once I get the one quadrant solution, right, it is done because of the circular symmetry. So you can simply extend it, you just generate it, you will get this equation, this graph, and then this graph and this graph. You don't have to solve it. If you want, you can solve it because we have sufficient number of equations. One equation I got Z4, you can subtract it to get Z2, you will get another equation. Once you get Z4 and Z2, you can substitute there in the above equations to find other. but you don't have to do it. Just calculate any one of them, and once you get one equation, right, the all other equations are like symmetrically we can get it. So now we got this entire region which is shaded there in purple color. That's going to be the region in which you can keep a mass so that the strings would not slacken. So we got the solution as a shaded area. This is a solution we have, entire solution. I solved it for first quadrant and I can generate it, you get the entire problem. So with that the solution is completed. I hope you understood. If you have any other ideas to solve this question, please let us know. This idea that I have explained it was given as a hint in this chapter, in this particular question, and I have generated it like this. If you get one more any other ideas, I will be more than welcome to discuss about it. We will get back to you again tomorrow with one more challenger question from Pathfinder. Until then, goodbye, take care, see you.